Okay, so good morning, everyone. We can continue our topic. Recently, we finished with heat transfer through conduction. So right now we are moving to the convective heat transfer. And I will refer once again to the general form of the conservation law that we have seen recently. And as you might remember, we had something like d dt plus the divergence of convection velocity times the advected quantity u equals divergence of the diffusivity times the gradient of u plus some volumetric source term. So if we are dealing with convective heat transfer, so then we know that the thermal energy is transported with the moving fluid. The idea is that we will be following the same procedure. So we want to select such a quantity u that will represent the physics that we want to represent. So what is this? Then u needs to be replaced by density, heat capacity, temperature. So in the linear case, it's basically the thermal energy that is contained within some fluid element. So let's do that. And if we do that, we see we get the following formulation. CP is heat capacity. Okay. Equals divergence of the thermal conductivity and that's wrong. Let's allow me to just put some diffusivity. And let's take the same diffusivity. Then we need to follow like substituting rho Cp T. I think you have already realized what would be wrong. Okay, so right now let's analyze the case that we deal with pretty often, which is that density is constant. So for example, we are dealing with a fluid, with a liquid, and heat capacity is constant. So basically a linear equation that we get. If we do it like that, then what we come up with is we can take rho Cp out of the derivation. We get something like that. Divergence of the velocity times temperature equals basically, let me write it this way. And as we have mentioned recently, you remember I have been defining, well, K or A, whatever it should be, as lambda divided by Cp, divided by rho Cp. So if we take it out, then obviously we've got K here times the gradient of T, QV, but you wouldn't usually write it like that in the equation representing the heat transfer, because you know that this one is lambda divided by rho Cp. So obviously, if this is constant, then these two terms simplify. And what we have is we are really having the physical heat flux that is that is represented in what dimensions? In watts per meter square, because it's basically how much heat flux goes through a specific cross-sectional area. Instead, in turn, this one is divided by the cubic meters, and we see that taking the derivative with respect to space from the flux, we add one more meter in the denominator, so the dimensions are fine. Okay, that's the simplification, like assuming that density and heat capacity are constant. Very, very often you will see that this is written and this is solved in the alternative way. Just let's omit rho Cp. Well, no magic, obviously, but very, very often what you do is you're writing the equation for temperature. So right now this needs to be QV divided by rho Cp. And very, very often when writing simple numerical codes, you will be solving the equation for the temperature. That's fine if you've got a linear case. But I want to underline and stress here that this one is often solved, but it's much, much better to be thinking about this equation and the general form. Since you know that this rho Cp T should represent our thermal energy, or specific thermal energy that is contained within the fluid element. But more specifically, it's like if Cp is not constant, then you actually define the heat energy a bit differently. You know that Cp for many materials behaves, well, in, let's say, such a manner that it very, very often it grows with temperature. And the proper definition of the thermal energy is nothing else than, okay, if we multiply it already by density, then it should be like taking the integral from some reference temperature, whatever the reference temperature is, we can actually define it, up to the, okay, it's thermal energy at temperature T. Then we need to integrate up to T, taking the Cp function that depends on temperature, and we're integrating the temperature. So basically what we are doing, we are defining some reference temperature, and we say that this is the zero level for the thermal energy, and then calculating the thermal energy is like integrating how much area we've got, how many joules we need to input to the fluid to heat it up to the current temperature, taking into account that Cp grows from one temperature value to the other. Questions? Clear? Good. Why do I mention that? I mention that because this already introduces nonlinearity into the system. So very, very often, if you're having cases like that, and you might often have cases like that, the Cp may change with temperature, your lambda may change with temperature, then it's really much, much better to not make any simplifications like that, but to always stick to the conservation law, and you know that not temperature is conserved in physics, but the energy is conserved in physics. So it's better to focus on energy conservation, and then what you need to do is you're basically writing the equation for convection of E. Here it's also a linear case because we simply multiply it by Cp. The most general form is simply saying, okay, let's write the equation for thermal energy. We will be diffusing thermal energy. And obviously, it does not have any direct or obvious relation with the temperature. So what you need to do in the numerical code is to discretize this equation, solve for ET, and then when you need to calculate any parameters, like for example lambda may depend on temperature. So what you do is the first step in a numerical procedure would be, well, discretize conservation law for thermal energy, then solve it. Solve for ET. The third step would be solve nonlinear, well, algebraic nonlinear equation for each mesh node. What kind of equation? E at t equals Et at, well, let's say some mesh node. So if you have solved this, you get the whole solution vector representing ET value for each mesh node. Then you need, for each mesh node, you need to solve an algebraic nonlinear equation to you need to properly select temperature T at the given node so that your energy really coincides with the thermal energy that you've got in your solution vector. By doing so, you retrieve the temperatures from the solution for ET. Well, probably the first step would be calculate nonlinear material parameters. Like, for example, this might depend on temperature. In some cases, you might want the density to depend on temperature. Like, for example, well, water changes its density with respect to temperature. Water glycol, probably even more. And then you go again to this step. You need to once again, or maybe not discretize the equation, but you need to once again assemble the matrices of the discretized problem, and then we are iterating that. We will be going into the discretization procedures and techniques, and then into the solution techniques for the equations in our, to some extent, probably still today, but in the more advanced fashion, we will be discussing this topic in the next meetings. Questions? If not, then one more remark, namely, what happens, and this is the question to you, what happens if we've got two phases? We've got some solid part of the domain and the fluid. And you are trying to solve this equation, or even simplified form, whatever, energy or temperature. Where do you impose the boundary conditions? As for example, the Dirichlet third type, second type, or third type.
The contact of solid fluid. And the contact it will be third boundary condition, third type.
So here.
Yeah.
Let me check if you understand me correctly. We are solving the coupled problem with the fluid and the solid in our domain. Okay.
You have to apply boundary condition, for example, on the bottom of the solid and on the inlet of the fluid. Because if you are solving coupled problem, then you've got like diffusion matrix in the solid and then convection diffusion in the fluid.
Exactly.
Because you are like trying to evaluate heat, convective heat transfer coefficients, like directly from the matrix, not assumed.
Exactly. Please never be misled by the intention to represent any boundary conditions here on the interface. It's not there. The boundary conditions, as the name says, need to be specified here. To be specified here. Okay, I haven't drawn the boundary and the inlet. Let's suppose it's here, but you're not imposing any boundary conditions here. So if anyone is telling you that they've got perfect correlation for heat transfer coefficient in the channel, if you're solving CFD with the fluid and the solid, the heat transfer coefficients are the result of the simulation, not something that you need to enter to the simulation. Why is that? Well, because you need to define what happens here. Everything else is represented by your equations. Specifically, you can actually apply this equation to the whole system, well, just saying that the properties are different in the solid and the velocity is 0 within the solid. And you can apply one equation to the whole domain. Well, numerically, maybe not the smartest way to implement that if you're representing these zeros, etc. Probably not, but theoretically it works. And what do the heat transfer coefficients at the interface come from? They come from the solution of the boundary layer. So basically from the solution of of this equation, but of the Navier-Stokes equations that you will be solving to account for the fluid flow here in this subdomain. And it's up to you and your mesh and representation of gradients, proper turbulence model if you've got turbulence in the system, to discretize the space, generate such a mesh to resolve the boundary layer profile properly. Because what happens with the convective heat transfer is that, well, let's assume that the fluid is not moving at all. What happens at the interface? Well, if you've got some thermal conductivity of the fluid, let's assume that we've got higher temperature here, lower temperature here. Probably you've got some, I don't know, some kink and different slope. But basically you would get linear distribution. What convection adds to the system? Convection makes the profile to be more convex. If you've got even stronger convection, then obviously the boundary layer will look like that. So you're increasing the gradient in the boundary layer, so close to the wall. That's why your fresh, hot fluid transports more energy and more easily to the interface. But certainly at the interface, no boundary condition, the heat transfer coefficients are the result of the simulation. And I think many people, especially people who know something about simulations, but they do not work with heat transfer simulations on a daily basis, then do not understand that they really forget it completely and they would like to input these parameters to the simulation. No, it's not how you do it, and it's basically wrong. What you can do, in turn, is you can define some alpha or heat transfer coefficient here. If you know that, okay, maybe you've got fluid in your pipe, there's the wall, and maybe you've got some surrounding air, well, in the infinity, so the reference temperature of the surrounding fluid, yes, then you would go again for this alpha T wall, which would represent the temperature here at that boundary, minus T air. That's perfectly okay, but not at the interface.